Howdy class. So today we're going to be talking about drawing Lewis structures and all the different things that go along with Lewis structures. Lewis structures are super fun. They're kind of hard, so you might have to review this a few times, but once you get the hang of it, you'll really like drawing Lewis structures, I think. Anywho, so these are our different steps from your textbook. You want to count the valence electrons. So you're going to add up the total for the polyatomic ion or the compound. So we're going to draw Lewis structures for neutral compounds and for polyatomic ions. So you want to add up all the valence electrons from each of those atoms and add in any charges. So any electrons that you need to add or subtract based on the charges on the ion. That's included in this step. Once you have the total number of electrons, now you're going to start by drawing the skeletal structure, which just means you're going to decide which one's the central atom and then connect everything to that central atom. The central atom is usually the least electronegative atom in the structure, except hydrogen is never a central atom. So even if hydrogen is the least electronegative in the structure, it won't be the central atom. So most of the time, you'll see central atoms of like carbon or nitrogen or sometimes oxygen, phosphorus, depends on what, sulfur, depends on what you're drawing. But it's always going to be the least electronegative. And things like halogens, so fluorine, chlorine, bromine, those are usually going to be on the outside, but not always. So sometimes chlorine or bromine are central atoms as well. So that's why we go with this general rule and not, giving you all the examples that we will then show you the exceptions for. Okay, once you have that skeletal structure, you want to subtract 2 electrons for each bond that you drew. So then you'll see how many valence electrons you have left. With those valence electrons you have left, you want to complete the octets of as many terminal atoms as possible. So these are usually those halogens that are on the outside that have lone pairs. You want to complete the octets by giving all those terminal atoms lone pairs. And then if there are any remaining at the end of that, you want to put them on the central atom, which usually is how we finish the octet for the central atom. But sometimes, as we'll see later, we can even put extra electrons on there beyond the octet. But we're going to start with the octet rule for today. And then if we still need to complete the octet of the central atom, we can use multiple bonds, so double bonds or triple bonds, to complete those octets. So we move one of the lone pairs from one of the terminal atoms and form it into a bond instead. All right, so these are the steps for a few different really common molecules and ions. So methane, we add up. So step 1, add up the valence electrons. So carbon has 4, each hydrogen contributes 1, so that adds up to 8. For carbon tetrafluoride here, carbon contributes 4, and each chlorine contributes 7. So 7 times 4 is 28, plus 4 for the carbon is 32. For water, oxygen has 6, each hydrogen has 2, we end up with 8. For oxygen gas, each oxygen atom contributes 6, so our molecule has 12. And finally, this is the cyanide ion. So cyanide, we've got carbon and nitrogen. Carbon contributes 4, nitrogen contributes 5, so that gets us to 9. And then the fact that we've got this negative charge means we have an extra electron in our ion. So that extra electron gets us to 10. So that's step 1 for all of these different molecules and ions. Only one's an ion, but I'm going to keep saying ions. So we draw our skeletal structure. Hydrogen can't be the central atom, so it's got to be carbon. Carbon is definitely less electronegative than chlorine, so it's the central atom again. Again, hydrogen can't be the central atom, so it's oxygen. This one doesn't really have a central atom, or this one, because they've only got 2 atoms in the compound slash ion to begin with. Then we subtract 2 for each bond. So there are 4 bonds in methane, so that's 8 electrons. So we subtract 8 electrons from the number we started with, which was 8, and now we got 0. So we're actually done with that one. But let's keep going. Let's look at step 3 for all of these structures. So we made 4 bonds in our carbon tetrachloride molecule. So that is 8 electrons. So we subtract 8 electrons off from our starting number, and we now have 24 left to continue drawing our Lewis structure. Same thing with water here. Now we have 2 bonds, so that's 4 electrons. We subtract that off, and we've still got some to play with. O2, we've got 1 bond, so that's 2 electrons. So we've got 10 electrons left to play with. And finally, cyanide, we have 1 bond, so that's 2 electrons. So we have 8 electrons left to play with. So, like I said, we were done with methane. So we draw our Lewis structure and make sure we have all of our electrons accounted for and all of our terminal atoms are happy, which is the case because hydrogen only wants 2 electrons around it. It doesn't want an octet. So we're done with that one. Next, we put our electrons on those terminal atoms, give them their lone pairs, and see what we have left. So this got cut off a little bit, but there are 2 electrons on there. So there are 3 lone pairs around each chlorine atom. So 3 lone pairs times 4 chlorine atoms is 12 lone pairs. So we've got 12 lone pairs, which is our remaining 24 electrons. So that's why there's nothing here for steps 5 or 6. We're done with this one as well. So carbon tetrachloride has 4 bonds, and each chlorine atom has 3 lone pairs. All right, let's look at water here. So we want to add electrons to our terminal atoms to get them to their octet, but hydrogen only wants 2, so we don't do anything in step 4 for water. But what do we do for oxygen gas? So oxygen gas, we put our lone pairs on. We have 10 electrons left over, so we can make 5 lone pairs. So we make 5 lone pairs, 3 on one of the oxygens, 2 on the other. So we're not quite done with that one. We'll see what happens next. But we'll stop there for now. That's step 4. And then step 4 for cyanide, we put all of our lone pairs on our terminal atoms. They're all terminal atoms in this case because there's only 2. So we put 3 lone pairs on nitrogen, and we put 1 lone pair on carbon for now because we only have 8 to work with. So we can put down 4 lone pairs. So we put 3 on nitrogen and 1 on carbon. We put 3 on nitrogen and not on carbon because nitrogen is the more electronegative of the 2. So we put more lone pairs on nitrogen than on carbon. All right, step 5 is where we add our electrons to the central atom. So water has oxygen as its central atom. So we have 4 electrons left. So we add 2 lone pairs to water. And now we're done with water. Or sorry, we add 2 lone pairs to oxygen, and now we're done with water. So that is our correct Lewis structure for water: 2 OH bonds and 2 lone pairs on oxygen. So step 5 is done for these 2 because they don't have a central atom. We called them both terminal atoms, so we did that step already. We've got our electrons distributed. But now, if we note, this oxygen atom only has 6 electrons around it. It has 2 lone pairs and then 2 electrons in the bond. So it doesn't have a full octet, but we don't have any more electrons to give it. So we have to take one of the lone pairs from the other oxygen and put it into the bond. So our final structure for oxygen gas has 2 lone pairs on both oxygens and a double bond between the oxygen atoms. So that satisfies our octet rule for both oxygen atoms and keeps us at the original number of valence electrons, which is 10. Sorry, 12. 12. Okay. You can count them up. There's 4 lone pairs in the molecule, so that is 8 electrons. And there's a double bond, which has 4. So that is a total of 12 electrons. All right. And then lastly, our cyanide ion, we ran out of electrons, just like with oxygen gas. So we need to put some of those electrons that are on nitrogen, some of those lone pairs, into our double bond. So we put 1 in, and then we get a double bond, but we still have, so then carbon will have a lone pair and 2 bonds, which gives it 6 electrons, so it still needs more. So we take another lone pair from nitrogen and throw it in as a triple bond. So now, with a triple bond between the two, both carbon and nitrogen have a lone pair and a triple bond. So the lone pair contributes 2 electrons and the triple bond contributes 6 to both atoms. So they have full octets. So this is another weird case where carbon has a lone pair, but this is because it's a cyanide ion, it's pretty reactive, so it's going to react with something that will give carbon an extra bond here, so it doesn't have a lone pair, but is sharing with something else instead. But for now, the cyanide ion has a lone pair on carbon and nitrogen, a triple bond between them, and we draw it in brackets because it is an ion, and we put our negative charge on there to show where our 10th electron came from. Okay, cool. That took a while, sorry. But I wanted to walk you through all those steps. So we can practice some more. So I'm going to do the examples of phosphorus trifluoride and carbon dioxide real quick. So phosphorus has 5 valence electrons, and each fluorine has 7 valence electrons. So our total is going to be 5 plus the quantity of 3 times 7. So that's 21 plus 5 is 26. We have 26 valence electrons in this molecule. Carbon dioxide, on the other hand, carbon has 4 valence electrons, each oxygen has 6, so 2 times 6 is 12, plus 4 is 16. So we've got 26 electrons in PF3 and 16 electrons in CO2. Now we want to draw our skeletal structure. So fluorine is a super electronegative atom, so that one's going to be on the outside, and phosphorus is going to be on the inside. That's our skeletal structure. We got a central atom and terminal atoms. Oxygen is more electronegative than carbon, so carbon's going to be our central atom. We put carbon in the middle, and oxygen are our 2 terminal atoms. And now we want to subtract 2 electrons per bond. So we had 26 to begin with for PF3. We've got 3 bonds, which gives us 6 bonding electrons. So we have 20 electrons left to work with. For carbon dioxide, we have 2 bonds, so those are 4 bonding electrons, so we have 12 left to work with. All right, cool. So now we want to complete the octets of those terminal atoms. So I'm going to draw my structure here again. PF3. Okay. So we want to complete the octets of our terminal atoms. So I'm going to give each fluorine 3 lone pairs. A little off the screen here, sorry. And this fluorine can have 3 lone pairs. They're a little funky, but they're there. So now we have 3 lone pairs. So how many electrons do we have? So we had 20 left to work with, and we gave each fluorine 3 lone pairs. So that's 3 pairs times 3 fluorines is 9 pairs, which gives us 18 electrons. So we have 20. So we had 20. We used 18. We have 2 left over for the next step. What about carbon dioxide? So now we want to put all those electrons on our terminal atoms. So I'm going to give 3 lone pairs to, sorry, that's a electron that became a line for some reason. But we have 3 lone pairs on each oxygen. So we had 12 electrons to work with, and we put 3 lone pairs on each oxygen atom. So that means that we used up 3 times 2 is 6 pairs. So that's 12. All right, so we used up all of our electrons for carbon dioxide. So let's move on to step 5. So step 5, draw my molecule down here again. So we have electrons all over our fluorine atoms. We have 3 lone pairs on each fluorine, and we have 2 left over, so those are going to go on our phosphorus. So now we have, we used our last 2, so we are done. And we can check our octet rule in step 6. Okay, so carbon dioxide, we didn't have any more electrons to satisfy the octet rule for carbon. So we've still got this structure to play with, where we've got these lone pairs and 2 bonds. And carbon only has 4 electrons around it. So let's go to step 6. So PF3 is done for step 6. There's 3 lone pairs on each fluorine and 1 lone pair on the phosphorus atom. And we're all done. They all have complete octets. Blech. So now for carbon dioxide, carbon only has 4 electrons around it, 2 in each bond. So we can't get any more valence electrons into our molecule, so we have to use the ones that we have. So I'm going to take 1 lone pair from this oxygen, throw it into a double bond, 1 lone pair from this oxygen, throw it into a double bond, and now we're going to have CO2, where each oxygen has 2 lone pairs now instead of 3, and there are 2 double bonds. So that is how we draw the structure of carbon dioxide. 2 double bonds between carbon and its 2 oxygens, and then 2 lone pairs on each oxygen. Cool. Alrighty. So your book is going to have you, or your homework, sorry, is going to have you draw the Lewis structures online, obviously, because it's online homework. So I just made a little video of what the builder, the molecule builder looks like on ALEKS, in case you haven't gotten that far yet. And I used a question that is not one that could be on your homework because we took the organic molecules off of your homework. So I'm going to make a structure that you won't have, so I won't be giving you any hints. So you can watch this little video of me playing with this molecule builder. So you can make different atoms, you can make different bonds. So the ethylamine molecule has 2 carbons, so those 2 carbons are both central atoms. So we didn't get quite that far yet talking about Lewis structures for organic molecules, but when you have multiple central atoms, then it's still usually the least electronegative. All right, so now I'm putting all my hydrogens on. There's 7 hydrogens that I need. So you just place the atom symbol and then type it in. So you just type in C for carbon, H for hydrogen. It's a little finicky, so it might take you a little while. Just be patient. It was a little frustrating for me too. Alrighty, so let's see what happens if I make a mistake. Oh no, I made a mistake. I didn't put my nitrogen on anywhere. So I hit the undo button and it goes away. And then I fight with it for a little while because it didn't want to let me put another atom there for whatever reason. So I hit undo again, and then it lets me put another atom there. Oh, I almost put H on again. Now we want nitrogen, because hydrogen can never be a terminal atom. Nitrogen is our third central atom. And now we want more bonds, and we have to use our remaining hydrogens. So I have 5 hydrogens already. So let's see what happens. So if I put on, so I'm counting my hydrogens, there's 7. So I don't actually need a bond here, so I use the eraser to get rid of the bond. Oh, right, don't need a bond. So the little 2 dots is our lone pair. So you want to use that for the lone pair. You definitely don't want to use this single one, because we're going to get to that in one of our later videos here today. That is a lone electron, and that atom with 1 electron on it would have been called a radical, and we don't want any radicals in our molecules. Unless we have to have them. So I didn't go through all the steps here, but hopefully this was just me showing you how to use this. So unless you're doing a section of your homework on radicals, don't use that one. Use this one with the 2 dots. That is our lone pair. Okay, cool. And that is it for Lewis structures. So I'm going to stop here and start another video.